you see my screen now?
Yep.
Yes.
Excellent. All right. Let me see if I can also get all of you visible at the same time. There we go. All right. Yeah. So thanks for having me. Like I said, there's some familiar faces. I hope I'm gonna be able to say some stuff that you maybe haven't heard before, at least for a few of you. So just a brief background. I'm CEO of Anotel. I've been working with machine learning for quite some time now. Mathematician by training, spent some time in the US at MIT and Berkeley, then worked for Recorded Future, building out our collection and analysis system there, and then started Anotel a couple of years ago, and it's grown into a pretty large company by now, which is fun. So enough of the ego slide. So basically, this is going to be the agenda for the 40 minutes that I have at my disposal. We're going to go. There's a few people who might need to mute. There we go. So we're going to go through, first of all, sort of, a brief recap of the workflow that you have to establish to work in machine learning in general. It's going to be short because I assume here that you're all in this on a daily basis. And then we're going to turn more specifically to sort of model performance, measuring data quality, how data quality is related to model performance. And we're going to do a case study on LiDAR annotations. So this is a kind of a dense, agenda for 40 minutes. So I'm going to have to blow through it a bit pretty quickly, but we're going to have some time to talk and ask some questions. And I don't know, if we don't make it through, it's maybe okay, as long as you get a chance to ask your questions, etc. So before we begin, and by the way, please interrupt me for questions. We're going to get to stuff that I think you're going to have questions about. So before we begin, we can first of all conclude that, machine learning is on everyone's mind. No need to repeat that. The problem is that it may be more of a pink unicorn than what you experience on a daily basis. So this is what a lot of machine learning practitioners feel like. I'm pretty sure you have these amazing things promised by this technology, and you might end up a sad donkey. Who knows? So in order to talk about data quality, we have to have an idea what this workflow is that we are dealing with. And basically, I see it as, there's quite a lot of steps to it. First of all, you have to, if we're skipping the whole, like, why are you doing this and what do you want to achieve? Because hopefully you have some sort of purpose in life. And instead focus on the fact, I'm sure some of you don't, because you work for super large companies and they might not have a clue why you're doing machine learning, but hopefully you personally know why you're doing it. So anyway, the point here is that in order to build a data set, which is kind of the sort of pillar of this, you need to start collecting data. That in itself is a huge challenge. Those of you from automotive here, we're going to go a bit more into detail on sort of calibration, time synchronization, etc. Huge problem. How do you equip your product with sensors in a way that makes data, achieve the necessary quality and standard you need for your product at the end of the day? You also need to start understanding what's in this data set. You can do sort of unsupervised clustering. There's tons of stuff that you can do to see if there are patterns in your data. It turns out it's basically impossible to learn something that isn't present in your data, which is, pretty obvious, but it's often overlooked. Don't try to learn stuff you haven't seen, or at least not using that data set, because that's going to be really hard. And then you need to define your learning task. And that's also, hard in the sense that by learning task here, my definition is sort of what is the ability you want to transfer onto your algorithm? What is it that you want your system to be able to do? And we're going to go a bit more into detail to that too in a moment, but there are many different things that, essentially depend on your data set. And then depending on, what amount of intermediate representations you need in your data. You're going to need to do some sort of annotations, maybe, unless it's sort of machine generated data that you can learn from. That's less common in computer vision, in my experience, because there's not really too many naturally occurring annotations in computer vision, as opposed to sort of ad recommendations or retail, which book should I buy? Well, you get annotations because people click your ads, and that means you get answers that you can learn from. Shooting pictures doesn't necessarily mean anyone tells you what's in them, which is kind of a problem, unless you can sort of farm this out to all your users like Google is doing. It's nice. Maybe some advice for Volvo Cars. You can put like a little captcha of road signs in your infotainment panel or something. Listen to the radio, but first identify 5 traffic signs. Maybe might not be super appreciated, but and then you need to define a label format and sort of how you want to express data. So from my perspective, the internet is a series of adapters, right? Like everything we do in data science, data engineering, machine learning is about fucking adapters. We have to write tons and tons of Python code, turning JSON into other sorts of JSON, essentially. Or even worse, maybe it's XML or some horrible format that people used to like. So there's a lot of that too here in the concept of data quality. And then there's maybe one of the least appreciated ones, which is going to be a big focus for me, along with calibration and so forth, and that is inter-annotator agreement. So that's essentially the question. Can humans do this thing consistently? Because it's super hard to teach a machine to do something that people can't do. For example, macroeconomics. We're never going to train computers to do macroeconomics because it doesn't exist. It's just people making guesses. So there's no way to learn signal that isn't there. And this is a hard problem for machine learning engineers, because frequently managers will point them to a problem and say, teach a model to do this. And it turns out no one was doing anything in the first place. So inter-annotator agreement and the presence of signal is super important and very, very hard to fully grasp until you face the situation where you're trying to train a system to do something that is essentially stochastic. For example, anecdotally, I know of a project that was done to automate sorting of documents at a large company. And it turned out there was pretty much a random allocation of the documents. So there was nothing to learn. The consequence was they just fired all the people who did the sorting because it didn't matter. But, it's an interesting consequence of machine learning. And then you need to collect tons and tons of labels, depending on, how precise your system is going to have to be. Unfortunately, deep learning is dumb. I mean, it's really dumb. Deep learning models are absolutely terrible at learning things in an efficient way. So you need tons and tons of data. And it's because of gradient descent and the fact that, sparse spaces take a lot of time to converge in, if you want to speak math. And then you get to model training. And this is where people typically think they are going to work. So you take engineers out of school who want to do deep learning, and then you airdrop those fuckers into the left side and they get depressed, right? So basically you're putting people into a situation that they not at all anticipated to be working on, and they fucking hate it. It's the worst part of their life. All they have to do all day is argue with people about what the meaning of things are so that they can label. And then maybe a year or two later, they get to train a model and it's over in 5 minutes. It's like being a teenager and you can leave the rest to your imagination. So there's all this work and then it's over in like 5 minutes. And then you start over again. So, this is a weird business we're in, and it's all about the data. And then obviously to make this worse, and today we're obviously going to focus a lot on the left here, but to make this worse, it's not even a linear process. Like you're going to fall back into previous steps all the time. you are going to have to define, if you're in automotive, you define your ODD, so your operational design domain. That's where you intend for your car to drive. And you also define your DDT, your dynamic driving task. And that's the, the work you're going to be doing in your ODD. And then you start sample this by driving and simulating. You start defining expected behavior, identify scenarios, you start training models, you start validating, you start launching into production and observe it there. And every time you move from one box to another, you realize you need to change something in a previous box. So in practice, you actually are bouncing around like a pinball between these things. And to make it even worse, you're doing this in a non-static environment. So you get new sensors, new objects, new behaviors, new regulations, new ML techniques. So you have this vortex of change, and a lot of people are sort of trained to think about projects as linear things where you do A, then B, then C, and out comes something at the end. Forget that. If you're approaching this that way, you're dead in the water. It doesn't work. There is absolutely no way you can approach this as a linear problem where you do a sequence of things. This is an iterative, nonlinear process, much more akin to research than to product development, period. Don't even try and argue with me. Not that I imagine you want to, but anyway. So some advice on this is like, assume it's iterative, invest in high engineering velocity. If you do not have low iteration time or fast iterations, your people are going to quit eventually. They will blow their head off or quit. Those are the options. Because there's nothing worse than being in an iterative nonlinear work stream that is slow. That is by far the worst thing you will ever experience. So I've done everything I can to streamline this. That has been by far the overarching priority for me in designing our engineering team. I don't care about, exact deliverables. I measure their iteration speed. And the faster they go, the more likely it is nice things are going to come out the other end. And it's a totally different paradigm for management here, because it means I basically don't look at what they achieve. I look at how fast they try. And I don't know if that necessarily has anything to do with data quality, but I assure you their ability to overcome those challenges is closely related to their iteration speed. And then you need to also maintain a list of assumptions. So some changes change everything, and they will happen. So there will be changes to your ODD, your DDT, your safety thresholds that will change a lot of things. So you will have to keep track of what is changing so that you can adapt accordingly. And then you need to understand data distributions. So basically, and this is an abstract concept, but humans are great at pattern matching. So if you take a chunk of the data that you're intending to process, look at it for days or even weeks, nonstop. Train your own neural network, because you have a pretty good one. If your network can't learn what's in that data set, you're fucked. You're never going to teach a computer to do it. There's no way. So my advice is to train your own neural network and try and imagine what the concepts and, things that are going on in your brain are, because that's what you're going to try and transfer to the model. And also look at the things that are confusing or hard for you, because that's likely to be confusing or hard for a model. So if there are things in your data set that you do not understand, do not be surprised if your model cannot handle it. Pretty intuitive, but often overlooked. I don't know how many of you have spent at least 100 hours browsing your own data, but if you have not clocked in 100 hours of data browsing, you should switch jobs or do it, period. And then the last thing is get a dumb baseline. And this is actually also often overlooked. People design these massive big bang projects, and they set a really high target, but they forget to actually connect everything end to end and get started. So my advice is always, even if it's MacGyver style with duct tape and, you know, whatever, just make it connected end to end, because you're going to realize so many things that you didn't think about. And it's so much easier to make it good, fast, safe if it works. If it doesn't work, you can't iterate. So this goes back to iteration and high engineering velocity. Make it work, then you make it good. So I talked, for example, with a high-level executive at a California AD company the other day, and he was so satisfied that their new VP of self-driving had shut down all these terrible ISO people, those guys that just write extensive documents that confuse the fuck out of the engineers. And the reason was that it doesn't matter until they make it work. If they can't make it work and can get the iterations where they have a dumb baseline, it doesn't matter what safe is. They need to get that first. And if they are prevented in getting a baseline by all those regulatory things, they will never get anywhere. And I actually buy into that 100%. Not saying they can ignore safety for very long. I'm a huge subscriber to the importance of safety, but I also firmly believe in establishing dumb baselines. So that was kind of a crash course in the overview. And then, like I said, this is going to be a pretty intense experience. We have 40 minutes, so I'm going to just steamroll into the next one. Do you know what your model needs to achieve? Ask yourself, you're training machine learning models. Do you know what performance you need to achieve? And the reason I ask you this is that it's going to be very, very hard to build a data set if you don't, because a machine learning model is effectively a compressed and compiled version of your data set. So if you think about this from an information theory perspective, and this is where it pays off studying theoretical math in university for me personally, you can basically imagine, or you can basically look at a machine learning model as a compression and compiler. So you have all these data points, and you need to find a projection onto a lower dimension space so that you can store the knowledge of that data set and then feed other data through that and reproduce predictions that generalize. So it's essentially compression and some compiling, depending on how you think of it. So you will never be able to learn anything that is not in your data set. It's like expecting a computer executable to perform actions that are not in the code. If you run some code through a compiler, it's weird that people are confused. I mean, no one gets confused that the code doesn't do things that, you know, the executable doesn't do things that are not in the code. Everyone intuitively understands that in order for the software to do anything, it has to be in the code. The exact same thing applies to machine learning, and the code is the data. So you're programming by example, and TensorFlow or PyTorch is your compiler.
It's actually even worse, sorry, disrupting, but you know, if you have a compiler, you get a syntax error. Here you will get an output, perfectly good output, which says nothing, right?
Yeah, exactly. I mean, it is indeed absolutely worse. And also machine learning models typically, or deep learning in particular, fails very silently. They are like, you know, ninja bugs. You don't hear them or see them. Yeah, it's a problem. So there are two approaches to machine learning that actually determine a lot about how you approach this. And this is ideological almost at this point. If you talk to, you know, George Hotz or someone like the Comma AI people, they are religious subscribers to the end-to-end deep learning school. They do not give a fuck about annotation or anything like that, because they just want to train a model to do the end learning task based on the raw input. You take the pixels and you turn the wheel. You have no idea what's going on in between. Basically, they just assume that the raw pixel stream can be translated into steering wheel movement. And it is not the business of humans to understand the petty things that go on in between. The only thing that matters is that wheel turning is appropriate based on pixel input. This school is pretty controversial because anyone who likes debugging things gets super freaked out that they have no idea what's going on between input and output. And I also actually happen to agree to this. So the other school is, I don't know even what to call it. I call it the school of intermediate representations. So basically, you want to get windows into your machine learning pipeline between input and output that are intelligible for humans. So some stuff like object detection, road detection, road signs, trajectories. These are intermediate representations that we intuitively assume can be used to determine what decisions to take. Whereas the end-to-end learning people say, yeah, those representations will manifest inside the network and definitely impact driving policy, but we do not need to know what they are. So,
comment here. We have been thinking a lot about this. My view is that the first one is really hard in the sense that it would require much more data because the problem is so huge. So the other one, where you have kind of broken down the problem, you need less data per component in that system, and the sum of those components on a data level is smaller than the end-to-end deep learning data need. I think this guy Andrew Ng has argued like this. He has written.
Yeah, I know Ang has this, but I disagree actually. But again, like this is, we could almost have a parliamentary debate here, and it'd be a bit akin to politics, because I don't think anyone really knows what's true or not. Not
okay, so at this stage, it's religion rather than scientifically proved that the dimensions, that you need more data in the first approach. That's a very interesting research field, actually. But
for sure, but it's not just about the data need. It's also about, the ability to a priori put constraints on what can happen. So your ability to predict boundary conditions for behavior is obviously harder if you have no intermediate representation, if that makes sense. Like if I want, so, okay, let me put this a different way.
Yeah, it's a bigger problem. I see what you mean. Yeah.
Yeah, I mean, to guarantee that a car cannot do a certain action in a certain situation is pretty hard if your entire driving policy is embedded into weights in a deep learning model that is completely end-to-end. Because from my perspective, and I don't claim to know everything about deep learning by far, but there's really no way to sort of, in practice, predict exactly what's going to happen for any type of input. Like, of course, it's deterministic to some degree, but it's also extremely sparse and very high dimensional. So it's not practically possible, probably. Whereas if you have a lot of intermediate representations, you can sort of put boundary constraints on behavior and say, if these intermediate things occur, if this, then that. Everyone who's done machine learning knows there's always room for some ifs.
But isn't this also related to priority? Do we want safety critical systems? So we know what input gets what output at a particular point, so we actually have some influence over it. So I guess it's more about which domain prioritizes what, and influence that research field, I suppose.
Yeah. Yeah, we could probably talk about this for the remainder of the session, but it's an interesting question, and it determines a lot about how you come at data quality, because essentially a lot of data set building is about, labeling intermediate representations and learning them. So part of why some people subscribe to the end-to-end learning approach is because they don't need to do all that tedious intermediate work. So even if you might need less data or more data, there's a lot of sort of corollary tasks you need to solve that you do not have to do in end-to-end deep learning. And I'm thinking hard about this. Obviously, I'm professionally biased to try and understand this, because if end-to-end deep learning wins, I don't need to label anything anymore, which is actually nice. Like, that's my goal with my company. But, you know, this isn't about Anotel specifically. So assuming we go into the intermediate representation camp for a moment, how do we think about data quality and model performance? So here is a bird's eye view of a car on a highway where there are a lot of potential vehicles around us. And we've labeled this scene 20 times. So here is basically people's perception of where cars are, as reflected in the number of people that found a car and where they thought it was. And as you can see, vehicles that are close by to your own vehicle, to Ego vehicle, are relatively crisp and found by everyone. And then the further out you go, the higher the variance in placement and the lower the probability that someone found it. And then, for example, if there's a parking lot next to the road, some people don't even bother because they don't care. And then, you know, so the reason I bring this slide up here immediately here is, like, in terms of expectations on model performance, it's very easy to express this in blunt terms, like I need 99% precision and recall on cars. And that's not true. You don't, because you don't give a shit about the cars over there in the parking lot if you're driving on the highway. So why waste a ton of money labeling those cars out there, and why push your machine learning team to try and find them? It doesn't matter, or probably doesn't matter. And then obviously there are weird edge cases where maybe the parking lot is very close to the road and it's not a highway. I mean, obviously you're not going to have, you know, direct access from a parking lot to a highway. If that's true, that's a weird country. There are some weird countries, so I'm not saying it's totally out of the realm of possibility, but, you know, not in Europe, at least. So then you can sort of make certain assumptions. And this is where data quality, model performance, and expectations, you immediately start, you know, if you have a little bit of imagination, you can see where this is going. It is very hard to define expectations and what they mean for data quality. If you have too blunt of a hammer, you're going to make a mess, right? This is a precision thing in terms of being very explicit about what you care about. Otherwise, you're going to end up wasting enormous resources, because there's so many things you can consider in computer vision. And again, like, I'm deliberately gearing this heavily against automotive here due to the audience, but, you know, this applies to other computer vision tasks as well. This is not unique to self-driving. And we also need to understand how we sort of can encode priorities. So this is something we've invested enormous amounts in, and that is basically sort of, and I've put some equations on here because I was told you're into that, and basically the purpose of this slide is to just give you an idea, like, okay, what can be a quality metric for a data set? Well, obviously you have sort of type 1, type 2 errors, precision and recall, and you have to decide. For example, you might have a boundary constraint that says, if I miss a car 20 meters in front of myself, the whole data set is essentially worth nothing. Because that could be the reality of your product. But on the other hand, if you miss a car that is, you know, 150 meters out and on a parking lot, it doesn't matter. So you need to find a way to sort of quantify data set quality, in a way that reflects your priorities. And you can do this by basically summing over all the boxes and then dividing by the number of type 1, type 2 errors, and you can put a weight to this. And then we can make it even worse. We can assume there's also sort of a correctness in the box. So we can create some sort of kernel that takes a perfect annotation or a perfect prediction or a perfect box, and then encode how we think about deviations from perfection. So basically, if I gave you 2 model predictions for your computer vision task, can you translate the difference between the 2 predictions into a number between 0 and 1? Which is basically a way of saying, can you sort of create a space in which there's a geometry to quality, a distance, even if it's very high dimensional? And are there hard constraints on that kernel? For example, there might be things you cannot violate, or your quality will go to 0 immediately. This doesn't have to be a continuous space. This can be a space with harsh limitations. But you have to figure out sort of what constitutes an acceptable deviation from intended performance, so that you can reason about what you tolerate. And I argue this has nothing to do with data set quality. This is you putting requirements on your machine learning model. And
But
then,
do I get it right that you have a ground truth in the scope here, or?
no, it's not your ground truth. It's your expectations.
Mm-hmm.
I mean, if you don't know what you want from your model, no one can help you.
Mm-hmm. Yeah, but how would you calculate those distances without ground truth? I mean, yeah, you can calculate distances of 2 different predictions, right? But what would they mean then?
I like the way you're thinking. Now you're getting into my world.
Sorry. Yeah.
So what is ground truth? And I'm sorry to put you on the spot here, but explain to me what ground truth is.
Yeah. There is nothing like the real ground truth, right? It's a sensor we trust more.
To dismiss it. I mean, honestly, tell me what it is.
Yeah, it's a sensor we trust more than the others, right? We use as a reference.
But what is a reference?
Yeah, that's still the labeled data.
And what are the labels?
Yeah, something which people as annotators like put on the sensor data.
And who decides what they put there?
Exactly, we as in the guidelines.
And what do you put in the guidelines?
Yeah, that's our expectations.
Exactly.
Mm-hmm.
So I don't depend on ground truth here. I depend on you knowing what you want.
Mm-hmm.
And you have to be able to tell me, if I show you a prediction, is this close enough to what you want?
Mm-hmm. Yeah.
And don't confuse that with the challenge of creating ground truth. The problem is you.
Mm-hmm. Yeah, and that's why we had a constant loop with you, on getting like it better and better in every iterations. Yes.
Exactly. So this is what I mean. And I mean, I'm an acquired taste. I'm not. I will never become a good politician. But the reason I push hard on this is that quality is the ability to replicate your expectations. And at the end of the day, if you don't know what you want, no one will give you quality.
Yeah,
So,
but you know what confused me? Confused me the thing that while putting expectations into the math, it's kind of difficult, right?
welcome to machine learning.
Yeah.
I mean, if you want to do something that isn't, replicating humans, don't do machine learning.
Yeah.
Machine learning is
No, we don't
inherently-
want to replicate humans. We want to be better than humans. Yeah.
I don't even
just
know what
joke
that
aside.
means. I mean,
Yeah.
if I agree, I mean, I agree with you in the sense that we can have sensors that are superior to human ability to see the world. And we can have perfect replication in a way that is not possible through lossy carbon-based processing. But at the end of the day, the objective function, the loss function, is determined by humans.
Yeah, so in this case, it would be actually, in our case, it's pretty simple, right? Because the human is out of the, well, sort of out of the equation. So the final outcome is like, say, number of accidents. And that's a very simple number and it's very measurable, right? And that can be like can be
if
beaten.
you ascribe to
Yes.
the end-to-end
Yeah.
process, you can basically say, yeah, I'm just going to throw more data at this until we stop running into people.
No.
You could even approach it as a reinforcement learning problem, but I hope you're not going to try and learn not to run into kids by applying reinforcement learning, because it's going to be a bloody mess.
Exactly, and I have only 2. Nope.
Yeah, right, exactly. There's a finite number,
Yes.
and people like them. I don't have any, so I don't care. But you know,
But
anyway.
Sorry,
the-
can I just say something? Don't want to be boring here, but it's time for next point in the agenda. If you want,
Yeah.
Raquel, maybe we should continue this, but according to the agenda, yeah.
So we're gonna wrap up in a couple of minutes, and there are many ways you can make this more detailed. I'll steal another 2 or 3 minutes, but I'm happy to discuss later, like what all the details can be that you can encode into sort of what is correct or not. But my point that I want you to take away from this is that data quality is the difference between what you expect and what you have in your data. And your machine learning model is a compiled and compressed version of your data set. So basically, data quality is your ability to express requirements. And then obviously your ability to satisfy those requirements in the data set. So of course, it's a tedious and, you know, demanding process to replicate your expectations in a data set. But you first of all need to know what you want. And then there are, you know, software companies, services, all these things you can use to achieve a data set that encodes your expectations. But it's all about the expectations. And then obviously, there are also other factors at play, like data collection quality, calibration, time sync, package loss. There's any number of things that can go wrong in the sensing phase. And that also will determine your ability to learn. So if you have, you know, terrible calibration, no time synchronization, you're frequently dropping packages when you log them on your vehicle or whatever, that's also going to impact data quality for sure. And then obviously, even if you know exactly what you want, you will have to have someone ensure that you can replicate your expectations at a large scale. So that is basically achieving annotator agreement across a large number of tasks. Also challenging, and you want to automate that and make that, you know, cost efficient. I'm a bit, you know, I'm not going to plug what I do too much, but that's essentially a big part. So you can reason about the impact of calibration geometrically. You can sort of translate, you know, angular deviations into what it means for your ability to do predictions. It's pretty straightforward, but it's surprisingly hard to do in practice. You will have, you know, potholes and things that make your vehicle experience some pretty uncomfortable G, and that can put things out of whack. You can, you know, have even boring things like material expansion and contraction due to temperature even. So there's a lot of stuff going on. So I was intending to do a little bit of a deep dive into sort of a case study for LiDAR. Basically, and I'm looking at the timekeeping here, and I expect to be interrupted any second, but I will keep going until they do. So basically, if you have a data set full of like bounding boxes for LiDAR, for example, such as this one, where you have, you know, a lot of non-linearly moving objects, urban scenario, tons of things going on, then how do you determine what data quality you need for this sort of data set? Because there will be small differences in interpretation. Here is 3 different bounding boxes made by 3 different people. Does this error matter? Well, it's insanely expensive to achieve perfection here. So probably don't expect that to be possible, but you need to find the right balance. And that is determined by, for example, trajectory tracking. So if you want to predict the trajectory of an object, it matters how it's oriented on an angular level. So your prediction, your perception system's ability to see the object will have a fairly large influence on the trajectory projected for the vehicle. So it might be that at high relative velocity, you need extremely precise perception. Otherwise, you will get a very weird trajectory prediction. So one key insight here, that is my last point, is that quality is actually extremely localized. And it's localized not only geometrically in the scene, but also with respect to the driving task. So the ODD and the DDT has massive variance in quality expectations. If you're approaching something at a high relative velocity, you will need extremely precise understanding. Whereas if you're trailing a car in a hunter target scenario on a highway, who gives a shit if you're 5 centimeters off? It doesn't matter. So this is my last key insight here is that, yes, you need to understand what your expectations are so that you can encode them in your data set, but you should assume it's very localized, high degree of variance across your space. So unfortunately, we don't have more time. I guess I can share the slides afterwards. And you
Sure,